Welcome to this new webinar series on how you can use SankhyaSutra Taral for your simulation needs. Like Ashwin said, I'll guide you through, the agenda for today is basically me guiding you through what SankhyaSutra Taral is, who we are as SankhyaSutra Labs, and what kind of facilities or features that SankhyaSutra Taral will give you so that you can add more value in your workflow. So I think most of you are already familiar with who we are, but just as a brief recap, we're a 30 plus strong technical team working in Bangalore. We were incubated in the Jawaharlal Nehru Center for Advanced Scientific Research about 8 years ago. And for the last 4 years, we've started working independently of the incubation center after securing investment from Reliance Industries. So we have a multitude of solvers that we're working on, but predominant, our, let's say, flagship product is SankhyaSutra Taral, which is an LBM based tool. So it's a Lattice Boltzmann based solver. And this brings me to basically a brief on what the solver is. So I think most of you will already be familiar with what Lattice Boltzmann methods are. So contrary to traditional methods of doing CFD by discretizing the Navier-Stokes equation and solving it, what we do here is start from the kinetic theory. Using the Boltzmann equation, we take a discrete form of the Boltzmann equation and we solve it on a lattice like the one you see here in this example. So your simulation domain will be made up of several lattice units like this. And what you're seeing is basically an example of a lattice unit in 3 dimensions. And the most basic difference between conventional traditional Navier-Stokes methods and Lattice Boltzmann methods is here you don't solve for the macroscopic quantities of pressure, velocity, and density, but instead you're solving for the statistical description or statistical probabilities of sets of particles being at a certain position on the lattice and traveling with certain discrete velocities in the directions that you can see here. So with the specific context of the example that I'm showing you, if you assume that a particle or a set of particles is present at the center of this lattice unit here, with the D3Q27 model, which is basically 27 discrete velocities in 3 directions in 3D space, your set of particles is allowed to travel along these arrows shown here. And what we do, the basic algorithm is that you track the evolution of these particle packet movements and incorporate your macroscopic constraints into the particle motion equations that you have. So the conservation of mass and momentum are built into something called the collision operator. And this collision operator is basically approximated by relaxation to some kind of equilibrium distribution of particles. Now, historically, Lattice Boltzmann, it doesn't have as long a history as traditional Navier-Stokes equations. And most people will probably know that Lattice Boltzmann solvers usually struggle when it comes to solving high Mach number flows, such as exceeding Mach numbers of 0.3 or some, or maybe even a little bit higher. So this is one of the focus regions for us as a software development company. And we basically use higher order models like the D3Q67 or D3Q167 model to simulate flows at high Mach numbers. And we also have a few other techniques that we use to make our solver more robust and numerically stable without the use of any turbulence models. So some of these are basically what you see here on the top left is we use something called the entropic formulation for the Lattice Boltzmann method, which is basically like implementing a constraint that is based on second law of thermodynamics, which says that entropy has to increase for any system. And in addition to this, we also use something called crystallographic LB, where instead of taking simple cubic meshes for our grids, we use body-centered cubic meshes to get a more accurate and faithful representation of any surfaces that we simulate. And like I said about the higher order models for high Reynolds and high Mach number flows. And in addition to this, we also have a few novel data structures and task decomposition methodologies that we use to make our parallelized algorithm more efficient. All of the details for these concepts can be found in the references that you see here at the bottom left of my screen. Right. So I've given you a brief of what exactly the solver is. I'll also show you a few examples that we've simulated in our company, so that you have an idea of the range of capabilities for this solver. So when it comes to fundamental flows, you can see here that we've done a range of flows ranging from low Mach number, low Reynolds number flows over symmetric airfoils, all the way up to, let's say, complex flow phenomena surrounding calculation of dynamic derivatives for moving geometries like the one you see here. So our solvers is basically very well suited to problems where you have a lot of these separated kind of flow structures, separated flows, or these complex flow structures evolving from the motion of geometries, like the SACON model here. And even at high Reynolds number, we're able to get a very good match with respect to experiments. Similarly, we've also done simulations of complex industrial scale problems like the flow past and generic automotive body that you see here on the left. So we see specifically from this simulation, you see that our solver is able to capture the flow separation and the generation of these large recirculation regions at the aft portion of the automotive body. And in other cases, we've done a simulation of a quadcopter, which is this is the model of the DJI Phantom 3. Even this is at a relatively lower Reynolds number, and the rotors are spinning at an RPM of 500. So what we see here is that what we saw is that we're able to capture interactions between the propellers and the flow patterns along the span of these rotors and the generation of these tip vortices and the interactions quite well. And we've also done a few cases where we apply our solver to the starting of compressibility. So this case you see here on the right is for the flow past a turbine blade at a Reynolds number of close to 1.5 million, 150,000, and Mach number of 0.65. And what you see basically is that the solver is able to accurately capture the development of the boundary layer and the macroscopic quantities. Like this is a plot of Mach number. You see that our results for evolution of Mach number, or the variation of Mach number along the chord of the turbine blade, is captured quite well in relation to experiments. And we've also done a few multiphysics simulations, like the store separation problem that you see here. And we've done a few transonic simulations of flows over blunt nose cones for projectiles. And one more very important and very in the moment kind of problem that we've also tackled is of aeroacoustics. What you see here is the simulation of flow over a transonic flow over a cavity. We're able to capture the variations of pressure, so basically pressure fluctuations PRMS at the floor of the cavity quite well as well. So basic feature benefits that you get from using SankhyaSutra Taral, unlike other traditional Navier-Stokes or other LB tools, is that our algorithm is basically devoid of any turbulence models. So what you are solving is the true physics of the problem. And in addition to this, our grid generation algorithm and all of these things are also automated, as you will see further in my in today's talk. And with the use of several techniques that I told you about earlier, our handling of complex and arbitrarily moving geometries is also very, very good. And we're able to handle flows that fall into the high Reynolds number, high Mach number range, where other solvers might struggle. So as a rule of thumb, what you can say is that you'd probably gain a lot of value by using our solver, where you have problems associated with transients and separated flows. And before physics testing, which is the phase where detailed testing and experimentation needs to be replaced with some alternative. So you want to reduce the number of experiments, but you want to do it with a very high accuracy simulation. That's where SankhyaSutra Taral fits in. And what you'll see throughout is that we are not exactly a replacement for RANS, because RANS is a very, you can say, a very low level description of your simulation problem. But when you want to get into the details of your flow, probably you want to analyze the fundamental flow phenomena that are occurring in your problem. That's where you'll find a lot of value with our solver. So now that I've covered what the solver is and how we are doing things here and what kind of value you can gain from it, I'll take you through the basic workflow that we follow when you run simulations with SankhyaSutra Taral. So our tool right now has the capability to take in any geometries that you can create with third-party tools. You specify a small set of parameters that you see here. These are all very simple, very basic parameters that you give the solver, and then based on these, the solver does your simulation. And you can either post-process with our own web-based GUI that I'll show you further in the talk, or you can use some third-party tools by downloading all of your simulation data yourself. So you either have the freedom to either choose to do your entire workflow with SankhyaSutra Taral, or if you want to have more freedom and explore the true boundaries of what your problem is, you can also go to third-party tools. In terms of geometry and import, so this becomes a very important aspect with any solver. So like I said, you'll be having the capability to import your geometries that you create with any third-party tool, let's say, for example, ANSA or SolidWorks or something. The only constraint right now is that all of your geometries that you import into Taral have to be of the stereolithography format. So this is the STL format written in ASCII. So once you've generated your geometry and converted into ASCII, you import it into Taral, where a few basic checks will be done on your geometry file, and it will give you a indication as to whether your geometry is good to go, whether the quality is good enough or not. The next thing is basically your simulation parameters that I told you earlier. Again, these are very, very simple and very straightforward when you look at when you compare it with, I don't know, doing a RAM simulation or something where you have to spend a lot of time. You might spend a lot of time just generating a grid and tailoring your simulation parameters to get the right fit for your problem. But with Taral, you don't have to do a lot of mind-numbing exercises like that. So for grid generation, like I said, it's automated for the most part. All you have to do is basically tell the solver what kind of resolutions you want in what areas. And this is done through telling the solver if you have surfaces in your simulation inside your domain, you tell the solver that you want such and such a cell size surrounding that surface and so on. And in terms of fluid properties, you only need to specify three basic properties, which are the density, kinematic viscosity, and molar mass. These are used by the solver to non-dimensionalize and convert to lattice units and vice versa. And basically, from the user's perspective, these are for non-dimensionalization. And once you're done with these things, you can also set up a range of save a range of simulation data through measurements, which includes probes, which are zero order or point measurements in space. You can save volumetric data, you can save surface data, and also the convenient thing with especially Taral is that you also get integrated forces and moment measurements directly from the solver. You don't have to do this as a part of your post processing. So this also simplifies your workflow quite a bit. And to define any measurement, you have three basic inputs, which is the sampling interval, the start and end time of your measurement, and any specific requirements such as the surface over which you want to save measurements or the specific volume over which you want to save measurements, that corresponds to each of the type of measurements. And in terms of global settings, all you have to do is provide the reference flow quantities and define initial and boundary conditions in a very simple, very straightforward way, and tell the solver whether you want to simulate for how long and if you want to save the state at some point. All of these will be covered in more detail as I describe take you through the workflow, and also in subsequent webinars. So I guess you can hang on for that. Yeah. So for today, I will show you how to simulate the flow over a NACA airfoil. The specific case that I've chosen is a NACA0012 airfoil, which is a symmetric airfoil with a 12% thickness. And it's at an angle of attack of 12 degrees, which is basically the start of your light stall regime at a Reynolds number of 50,000. So the simulation domain looks a little bit like what you see on your screen here on the left. I've chosen to have a domain that extends in 5 chord lengths in front of the leading edge of the airfoil and 10 chord lengths in downstream of the trailing edge. And the domain extends 2.5 chord lengths on each side in the vertical direction, and in the spanwise direction I've kept a length of 1 meter. So the chord of the airfoil is going to be 1 meter, so this gives you an aspect ratio of 1. So one very important thing when you do quasi 2D simulations like these is your end wall boundary conditions. So in today's specific case, I'll be implementing a periodicity condition for the spanwise direction. So this means that you can also reduce the spanwise extent of your airfoil, because you're saying that the simulation domain basically extends to infinity on both sides. But in reality, what you're doing is simulating a very small part. So this reduces the computational cost of your problem. For the initial conditions, I'll be assuming, I'm sorry, I think there is a typo here, but since the Reynolds number is 50,000, it's fixed, we'll calculate our initial and boundary conditions based on these. The initial condition, there is a typo here, it should be 0.75 meters, which corresponds to the Reynolds number that I mentioned. And we'll set the inlet with the same condition, with constant velocity. For the outlet, we'll give a constant pressure of 1 atmosphere, and the surface of the airfoil will be treated as a no-slip wall. The lateral domains, like I said, will have periodicity, and the top and bottom will have free slip condition imposed. So with this, I will transition you to the actual interface of our solver, and I'll show you how you can do things. So once you register, or basically the way to access your solver is to go to this URL. You'll be presented with the login screen where you can enter your credentials. And if you're a first-time user, you'll also be presented with the end-user license agreement that you have to agree in order to access the tool. So once you enter your credentials, you might be shown a message like this. This basically means that I've logged in through other browser as well. You can click OK, proceed, and this takes you to your dashboard. So the dashboard is where you will find all details about the different kinds of projects you have. And if you've shared with any other users any of your projects, or if they've shared any projects with you, then you can also access those. So I have 3 projects that have been shared with me by other users. So if I go back to my projects, you'll see the list of all the projects that I have created. Now, as a new user, your dashboard will be empty. So the way to start a project is by clicking on this new project button. And this opens a dialog box where you basically tell the title of the project. So in this case, let me give you a appropriate title. Let's say NACA0012 demo. And I give a description that is appropriate for this problem that I'm doing. So I'll say it's a light stall simulation at Reynolds number of 50K for a symmetric airfoil. The description can be anything. So you just have to give a message here that will let you, understand what each project is without you having to, go through the details of it. So once you click on the create project, you see that your dashboard has been populated with the project that you just created. And it has all the details that you gave it. So the name, the description, and it has this information about the date and time at which it was created and last updated. And this column here, it shows you the status of your project. So basically now I've just created it and I've added nothing, so it says not run. So to actually start working on your project, you click on this open in workspace button, and this will lead you to your workspace. um, so the first thing that you do when you enter the workspace, you have this simulation tree here with all the options that you need to input in order to run your simulation. So the first thing you do is import your geometry, or you also have the option to create your own basic shapes. So if you want, you can just import your airfoil geometry and then create a box for the domain here. So since I already have the geometry ready, I'll import it. So once you click on this import button, it'll show you, it'll let you browse, and I'll open up my geometry, which is this one. So once you choose the STL file that you want to import, it will show the name and the size of the file here. So one thing to keep in mind here is that since this is a web-based tool, if you are importing very large geometries, it might take a little while to actually load the geometry into the workspace, because the data needs to be uploaded to the server first. Yeah. So you will be shown a message here if your geometry is past a certain file size. So once you're satisfied with this, you can click on this tick button, and that imports your geometry into the workspace. So this is what my geometry looks like, as I showed you earlier. So you can zoom in, zoom out, pan around, and you have these basic view control buttons that you can use to manipulate the camera view. So I told you that we are simulating a flow past a NACA airfoil. And one important thing that I didn't mention earlier is that we will be using something called a multi-resolution strategy. So there are two different discretization strategies that you can follow with Taral. The first and most simple one is called the single resolution strategy, where your domain is basically discretized and all the cells in your domain are of the same size. So although the creation, I mean, the discretization step is simpler, with the single resolution grid, it will most likely be true that your simulation is going to be computationally more expensive than it actually needs to be to get that level of accuracy. But when you use something called the multi-resolution strategy, which is what I'm going to discuss today, you can set up your simulation to have multiple levels of resolution, where each level has cells of the same size, but the sizes at different levels are different. So this allows you to have localized regions where you have a finer grid, and coarsen out the grid as you go to some region, let's say very far away from your solid body or something, where you expect not to see large gradients or any important flow phenomena. So you can retain the same accuracy as a single resolution strategy with a very low computational cost. So one example is of the case that I'm going to show you right now. So with the single resolution strategy, I get for a finest cell size of 8.3 millimeters. This is about 125 points for the chord of the airfoil. I get a grid that is composed of nearly 160 million points. But for the same resolution close to the airfoil, strategically coarsening it out towards the domain walls, I have reduced it using the multi-resolution strategy to 17 million cells. This is almost a tenth of the single resolution. So this will probably give you a computational time reduction of the order of 10. So yeah, I'll take you through how you can set up such a simulation. Right. So we've imported the geometry here. Now I showed you that we were using a cell size of 8.3 millimeters close to the around the surface of our body of importance here, which is the airfoil. So here from our geometry tree, I will click on the airfoil patch, and then I'll say set a resolution to this, and I give the value of 0.0083, which is 8.33 millimeters, and I click tick. It basically saves it. So any surface that you set with a specific resolution will be shown with a blue tick here. Now, to ensure that you have a multi-level simulation, the next thing you have to do is specify the coarsest cell size. So you do this by specifying the project level resolution. And let's say I want a project or coarsest cell size of 20 millimeters. So this will give me 3 levels, like you saw in the sample image that I showed you just earlier. So this, you set the project resolution to 0.02 and you save that. And then you can go back to defining your simulation domain. Now, one more thing of importance is basically here is you tell the simulation that you have multiple regions here. So a region is basically any volume that is disjoint from other volumes. So in our case, we have 3 such regions. One is the bulk of the airfoil. The number 2 is the bulk of the fluid, which is basically whatever is bounded between the domain walls and the surface of the airfoil, and the third is the outside of the domain. So of these 3 regions, we only want to simulate region number 2. So this is what we will set up in our simulation. So we define 3 regions. The first is the outside region. You say which geometry it is relative to. Basically, what you have to do is tell the solver that this region has some point here that identifies it. And since we don't want to do any simulation in this region, we'll set it to the kind vacuum. So this orange dot here is the point that you're seeing here. You can increase or decrease the size of this point display based on your convenience. So I set this, and similar to this, I'll set up the other 2 regions as well. So the second one is fluid, and let's zoom in. So the point 1, 0, 0 is inside the fluid domain. So I select here kind simulate, I save it, and then there is the final one, which is the airfoil bulk. And again, this is of kind vacuum because we don't want to simulate airflow inside the airfoil. So once you've done with setting up the regions, the next thing you do is set up something called a brush. So a brush is basically a region in space in the fluid domain that you assign a specific cell size to. So let's say if you want to refine the wake of your airfoil, you will create a brush by clicking on this plus. You give it the min and max points of the diagonal of the brush. So this will be your min point and this will be your max point. And assign the resolution that you want in that brush. So for this case, I won't use a brush. And still, that's how you will set it up. So once you're done with that, the next thing to do is define the material properties. So by default, you will have a library of materials. So right now it's like 3 materials here. You can create your own custom material and basically click on this plus sign here next to custom materials, and you give the properties that you want. So the kinematic viscosity, I'll say is 6 and molar mass of 97. All of these correspond to air around room temperature. And we tell the solver that it's a gaseous fluid. Let's say I give this material some name, my material. I click on the tick button. So this my material got added. And if you want to edit it at some later point, you can also do that. So once you've added the material properties, the next thing to do is define the initial conditions. Let's say I want a uniform flow, which is corresponding to the free stream. So I will set this to my free stream velocity that gives a Reynolds number that I want, which is 0.75 meters per second, and room temperature and static pressure, which is equivalent to atmospheric. So my uniform flow condition has been added. And one more nifty feature with Taral is that whenever you import or create a geometry, it will populate this list of boundary conditions that you set automatically. All you have to do is set the specific conditions that you want. So here my X-min wall is my inlet. So I will assign the inlet condition. The from and to regions basically define where your boundary points are applied. So the boundary points are applied in the to region right next to the surface that is separating the two. So here it's outside to fluid, and I want speed of constant velocity of 0.75 meters per second. So that is set. X max is my outlet. I will set it to 1 atmosphere, which is also set by default. And the Y min and Y max faces are the top and bottom, which I want to set to free slip. So this surface will highlight whichever surface you are applying it to. So Y min is the bottom wall. And since I want to apply the same condition to the top wall, what I'll do is I'll copy this boundary condition and I'll assign it to Y max. So I click on selected Y max and I click on copy. So you see that Y max also got automatically populated and it's taken the correct surface name and everything. The next thing is to set up my periodic boundaries. So in the type dropdown, I select periodic and select the surface. And again, similarly, I'll use the copy functionality to the Zmax. So both Zmin and Zmax have been set to periodicity. The last thing is to set a no-slip wall. This is basically called wall in Taral to my airfoil surface. So once you're done with all this, the last thing you have to do is to set up your measurements. So one important thing to note here, when you're using the web-based GUI, whatever you set up as probe will be available to you as a monitor to monitor the similar progress of your simulation. So let's say I want to set up two probes, both in the wake of the airfoil, one very close to it and one a little bit further away. So the first one, let's say I want to save only velocity and pressure. So we'll say this is at location 0.5, 0.05, which is directly above the 75% chord location of the airfoil. And I say that I want to capture samples every millisecond, let's assume. So I give a gap time of 1 millisecond. You can also set the start and stop time to some specific values. So the start time is when the simulation time at which your measurement will start getting saved, and this is when it will stop being saved. So let's say I just want to save for the entire duration of the simulation. So I disable that and I click on the stick to save it. Similarly, I'll create another one. Call it pwake 2. Let's say I want to save density as well for this. With the same sampling interval. And done. Similarly, you can also set up volumetric measurements, which basically saves data for the entire simulation volume. And here, let's say I save velocity and pressure. And for this, I will, since I know that it's going to be a lot of data, and I might not have access to a lot of storage, I'll say I want to save only once every 0.1 seconds. So I say that. And similar for my surface. So for the surface, one additional input is to select the simulate region at which you want to capture your surface quantities and the surface over which you want to capture it. So NACA0012 is my airfoil surface, and I want to save data on this surface corresponding to the fluid region. So that's what I have assigned here. And like I was saying, you can save integrated quantities, which basically calculates the forces in the three principal directions and the moments and puts it in a CSV file. So once you're done with all this, the last thing to do is to give your global simulation parameters. So let's say I want to run a simulation of 100 seconds. And this is where I can also input the parameters for my cluster use or my simulation job. So most of you will be using high performance clusters. So here you can input, let's say, the wall time you want to give and the number of cores that you want to use. So for my case, let's say I want to give a wall time of 24 hours and I use only 128 cores. And like I was saying, there's the option of setting something called a restart, which basically saves the state of your simulation at some specific intervals. So let's say I want to save the state every 10 seconds. So I'll give a restart gap of 10. So what this basically means is after the 10 seconds of simulations are complete, the solver will save the state of the entire simulation in a specific place. And if in case you stop the simulation for any reason after that point, or your simulation crashes because your connection to the HPC was lost, then you can always restart from this point in time rather than having to launch from the zeroth time step. So once I've set all that, I save my simulation parameters, and basically I'm ready to start my simulation. So before this, what you can also do is use this generate feature, and this will generate what is called the input Python script. So this is just a verification step. So this is a Python script that basically contains all the information that you fed here, and this is what will get supplied to the solver. So you can verify whether everything is set correctly based on your inputs. And once you're satisfied with that, you can go back here, click on simulation, and then click on launch. So once you click on launch, a pre-submission check is done that will, go through all your inputs to see if they're as expected. It's basically like a sanity check. So if there is any problem, it will give you an error message here with the specific problem. So once it has passed, your simulation job will be submitted to the supercomputer or any other maybe even workstation that you're running on, and it will show you the status here. See, now it says it is running, but in case you don't have enough resources, it will say that you are in queue, or it will say that there was an error. Now since this is running, you can have a look at the log, which basically has details on the current state of the simulation, and in addition, it also has these details about the parameters that it has used, including the grid generation parameters. So it's saying that my probe was snapped to the nearest point, which is this point, which is basically the closest point to wherever I had defined it. And my volume and other data files can be found at these specific locations. So as the simulation progresses, new lines will be written here indicating that such and such an iteration number or time has been elapsed. So I have another project that I ran with this, which is at a more advanced state. So I can show you what exactly it looks like. So like I was telling you, whatever you've saved as probes will show up in monitor plots. So if you click on this monitor plots, you'll see that there are a bunch of XY plots for each of the quantities that you've saved. So here you see you saved 2 probes, and these are shown here: pressure, velocity components, and only 1 probe had density, so only 1 line here. And your integrated forces are also displayed here. So you can basically just monitor lift and drag for your airfoil from this monitor plot. Now, let's say your simulation is complete and you want to start processing your data. So what you can do is click on this post-processing tab here. And for now, you have 2 basic options, which is either to create a slice of your volumetric data and visualize it, or you can, say you want to visualize your surface data that you saved. So to create either of these, what you do is click on this plus button here, and a pop-up will be shown where you enter the details. So let's say I want to slice in the Z plane. So I'll say slice_Z, and you'll see based on these normal values, basically a demo plane is created, which will help you visualize where exactly you are slicing. So let's say I want to keep this location. It's normal to the Z direction at the point, and it's the plane has an origin at the point 0, 0, 0. Now, since this post-processing job is also submitted to the cluster or workstation where you're running it, you will be able to input the resources required here as well. So let's say I want a wall time of just 2 hours, and I'll use 10 cores here. So you can give the input like that, and the start and end frame basically come from the availability of your simulation data files. So because I just launched my simulation, it's probably not at a time step yet where any data has been saved. That's why it says start frame is 0 and end frame is 0. So even if I submit the post-processing job now, it's going to give me an error saying that you will not be, there is no data to process. But once your simulation gets to a far enough point where you have, multiple frames, the first available frame and the last available frame will be shown to you here by default. But you can also change these based on your requirements. So let's say if you want to start processing only from the 100 frame and until the 200 frame, so you can input 100 here and 200 here, and then click on this tick button. So this will launch a post-processing slicing job. Similarly, you can also launch a surface job where you select your surface measurement and the patch and give the same inputs. So I'll show you an example of a project that I've already run with which has some post-processing. So I created a slice for this, and you see that the slice is automatically loaded. And based on your internet connection, you might find that this is a little bit glitchy. But if you have a good internet connection, which is fast enough, then this will be a very smooth affair. So once you created slices, you will get options like these. This second dropdown is basically the frame number that you're visualizing. So you can choose from all the available frames by opening the dropdown and clicking on the frame that you want. I think there's a very slow internet connection. So. Yeah, so the other options are basically the type of visualization you want to do. So this is a surface. You can even choose to visualize surface with edges. So surface with edge basically means that your slice data will be shown overlaid with the grid that was generated for this file. What you can also do is show just points, or you can hide the thing entirely, or you can just visualize the wireframe. So wireframe and points will show you the point data here. And once you have chosen this, you can also select different color maps. So right now it's saying it's warm to cool color map, and there are a set of 7 or 8 color maps that you can choose from based on whatever your requirement is or whatever you like. So let's say I want to choose a rainbow color map, and I'll say I want to color based on velocity x contours. So this will show me the velocity x or its distribution inside the simulation domain like this. And with these play buttons and pause buttons, you can basically loop through all your available frames of post-process data. So this loop button will enable or disable, like jumping from the last frame to the first frame and replaying everything. You can also save images directly by clicking on this camera icon here, and it will save it as a PNG image. So for those of you who want to, do your own post-processing, you have this download button here next to the simulation tree item. Clicking on this will give you options to choose which data you want to save. So if you say select all and click download, a zip file will be downloaded to your local machine, wherever you are running the browser. And once you've downloaded this, you can use any third-party tool, let's say ParaView or something like that, to visualize your data. Yeah. So this basically covers the workflow for a simple case of simulating flow past a NACA airfoil with periodicity in the span-wise direction. There'll be more webinars for all the different features and functionalities available through SankhyaSutra Taral in the following days or weeks. And if you're interested, you can keep in touch and attend the subsequent webinars as well. So I think we're open for questions now. So if any of you have any doubts or any clarifications that you want, you can post in the chat or maybe unmute yourself. Okay, post in the chat.